Hi, I'm Metta Spencer. Today we're going to talk about concrete. And this is about the third or fourth, well, at least the third conversation I've had about the subject. And it's one that the more I listen to, the more fascinated I get. And not because everybody necessarily agrees, because it's a very, very important topic. Something like 8% of the carbon emissions to the atmosphere comes from concrete. So, because concrete is such an important material for building, it's the most used of any of the substances except water for construction in the world. And therefore, we should give some thought to what it's doing to our global warming issues. And there are people who think that we can reduce the amount of carbon that we emit in various ways. Some of them think we should use less concrete, for one thing. Other people believe that there are ways of capturing carbon dioxide in the atmosphere or in some other way and embedding it in concrete. So this is a bit of a controversial issue, and we're going to talk about it today with some people who know a thing or two on the subject, which I certainly don't. Karen Scrivener is a materials chemist who's known for her pioneering work in cementitious materials. She's the head of the Laboratory of Construction Materials at the École Politique Fédérale de Lausanne. It's in Switzerland, and has served as the editor-in-chief of the Cement and Concrete Research Journal for 15 years. Good morning, Karen.
Good morning.
In California is Peter Fikowski, who is a physicist, an entrepreneur, and he founded and was the chairman of the Foundation for Climate Restoration. He's a philanthropist because he's made a bit of money by his many patents, and he is the author of one of the most interesting, if not the most interesting book I've read this year, and if not the last several years, called Climate Restoration. I'm urging everybody to go read that book.
There you go.
There it is. Very good, Peter. Thanks. And Martin Halliwell is a little closer to home. I believe you live in Toronto, do you not, Martin? And he is
in Ontario, though.
Okay. He's president of Footprint Engineering, which constructs buildings and heavy civil, mechanical, electrical, waterproofing systems, foundations, etc. So he has thoughts and has done innovative work with concrete. Now, the shows that we're doing these days, we ask that some members of the Canadian Pugwash Group be present, because we like to have people from the Pugwash Group inquire and query our expert panelists today. Tariq Ralph is nowhere near me. He's in Vienna, and he is an expert on nuclear matters, having worked at the IAEA for a long time and is a consultant there. And in Toronto is Adele Buckley, who's also a physicist and engineer, and very active. Both of them are very active in the Canadian Pugwash Group. I know that not everybody believes that that it is realistic to try to create concrete that is carbon negative. I'm pretty sure we have at least two different points of view about that here, and maybe there are a dozen points of view. I don't know. Karen, well, let me ask you, what do you think about the current status of all this experimentation and innovation going on, claiming at any rate and hoping to be able to produce carbon negative concrete?
Well, I think there's a lot of things you can do to reduce CO2 emissions from concrete. And we should remember that already it's quite an environmentally friendly material. It's just because of the enormous amounts we use that it all adds up. So you're not going to make things better by replacing concrete with something else. But the idea that it can be totally carbon negative is really not realistic, because most of the emissions are coming from the breakdown of limestone. And you can't make cement without limestone. And, lots of people are claiming, well, it combines CO2 with calcium, and of course it does, it recarbonates afterwards, but you're never going to absorb more CO2 afterwards than you emitted in the first place. So, you have to look at how much calcium is out there to be carbonated. There's really very little. And we have a paper we're going to submit soon, which estimates that probably the amount of CO2 you can reabsorb by carbonating, calcium in concrete and things like that is probably roughly about 1% of annual CO2 emissions. So that's not nothing. It's quite significant, and it's certainly something we should be doing. But you're certainly not going to go to a product that's totally carbon negative.
All right. That is planting a flag. Let's say, which of you would like to, I'm going to go the easy route and slide into this by asking Martin. Martin Halliwell, you have long experience in construction using concrete rather. And tell me what your own view about this subject is.
Excuse me, Meta, but yeah. I think it might be useful to clarify the issue, because Karen said very important things about cement, which I don't think anyone would disagree with much. I wouldn't, certainly. But there's, of course, a big difference between cement and rock. And concrete consists of two separate parts, the rock and the cement. So maybe Martin can talk about one or the other of those.
All right, Martin.
So
clarify matters for us.
So I would obviously fall on the side of doing a better job with concrete. And what's true today is concrete's very porous, and we see a lot of over design with concrete. And so my objective is to try and contribute by a unique mix design I've come up with that arguably would last 1,000 years instead of 25. So the 25-year stuff that we're seeing in Toronto, we see a very porous product, and so then we're rehabbing, and you have to consider the rehab effort and all the related diesel and fuels and patching bag materials that are out there. So if we can do a better job with the original mix, I just tell people how to adjust the mix. And I'll mention two products that I believe in. One's basaltic fibers, which is twice the stiffness of steel fiber and renders things crack free. And the other one is nanocolloidal silica admixture, which is becoming a rage down in the States and with bridge decks. But I think the over design of rebar is a big problem. We have this idea that we have to do crack control, and unless you need a tension or compression force, why would we put in more rebar than we need? The figures show that it's 1,000 kilograms, and I'm metric here in Canada.
People will need to know more about what rebar is. I assume it's the metal bars that they use for reinforced concrete, and you say it's to prevent cracks. Could you explain what rebar is a little?
Yeah, so it's usually a steel bar. It's got a big footprint. The 1,000 kilograms of steel is 6,000 kilograms of CO2, whereas 1,000 kilograms of cement is 1,000 kilograms of CO2. So I go after the 80-20 rule. I'm a big advocate of not over designing things. And then I went after that mix design. But my patents are all below grade because I'm a foundation specialist, and that's where I've seen the most waste from the 1980s to now. We've seen tremendous over design, which I have opinions on why that's caused. But we just try to do something in the way of value engineering. I don't design those buildings. I don't do detailed design, Matt. I do value engineering. So I tell people which systems to pick. I believe that crack control is a big problem with floors and slabs and this whole thing with over design. Can I comment about our Toronto subways? Do I have time?
Sure.
Yeah. So in the 1970s, we built subway walls at Yonge and Finch that were 16 inches thick. And there's no tile that's off those walls, and that's 50 years. And now we see subways that are 1 meter walls, 1 meter slabs, and 265 kilograms per cubic meter of concrete in rebar design. So those things in front of certain excavation support systems are causing our P3 budgets to be twice what they need to be. And I think for the taxpayer and for the good of society, that we need to point these things out. And it might be hard to change, but I do have a meeting with City Hall in Toronto on February 6th that I hope to make some changes in the way the underground bathtub laws work. So in Toronto Meta, they thought they had a problem with water going to Ashbridges Bay. So they said, we don't want any combined storm and sanitary in this anymore. So they created a practice of pouring 5-foot thick raft slabs in the bottom of every parking garage, new parking garage in Toronto. And that's something I'd like to change, because in that 5-foot raft slab in the bottom of Toronto, which we never did in the 80s, there's 265 kilograms per cubic meter of rebar.
I was hoping you could speak a bit more about the role of rebar within crack control. I thought Meta mentioned you saying that rebar mitigates cracking, but I had heard that it actually results in more cracking over time, especially in climates where you have significant temperature swings of cold, hot, and that the expansion and contraction of the rebar is what's causing a lot of structural failure in concrete materials. Is that true, or is it a myth in regards to these materials?
I think there's some truth to that, but generally, these things are not in sidewalks. They're in interior situations that aren't freezing. We have a porous concrete cover on top of rebar. So what happens is the 1.5 inches or 2 inches of concrete cover that they think is protecting this rebar is leaking in the salts, and our infrastructure falls apart because of it. And so, they can put bituminous waterproofing on top of that, and they can do all these things. But when it's a common thing that the rebar is crack control. And so they put lots of rebar in. And the other thing I'll mention is in our infrastructure projects, the engineering industry is consolidated, and they charge 8% of hard cost. And they use the same details all the time. So there's no incentive to reduce the thickness of subway walls in Toronto.
I think over design is certainly part of the issue. And, there's many aspects to this. Martin's come up with some of them, but it can be as simple in buildings as, rethinking the layout. Many high-story buildings, because they want to have big areas open on the ground floor and then transfer to housing. They have incredibly complicated structural loading systems, which lead to a very wasteful use of all materials, concrete and, of course, steel. And I would like to point out to Martin that, emissions of cement may be close to 900 kilos per ton, but that's not the end material we use. The end material we use is concrete, and that's got much, much lower emissions again. That can be down at around 200 kilos per meter cube, which is 2 tons. So 100 kilos per meter cube. So, it really is a very good material compared to steel. We're overusing steel. And long and short of over design, I think there's 2 factors here that really need pointing out. The first one is that people are just so brainwashed that they've got to be safer than safe. We have building codes which already have huge safety margins put in, but then people think, oh, well, we can't design up to the code. We should only design to about 80% of what we can do in the code, which is nonsense, because these codes have been very carefully worked out, and most people will already agree they're over conservative. The other thing is that the long and short of it is that the time we pay engineers to make designs and to optimize things is far less than what it costs to put in some extra concrete, because concrete's a very cheap material. So, if people are not sure, they say, well, let's put in a bit more. And I think there are now coming out new tools which can help people to use concrete better. And I think all of these are very positive trends. And I think we can really imagine that by cutting down over design, we have possibility to save 30-40% of the CO2 in concrete. Mm-hmm. And, my philosophy is, we have to work at all the different levels. We have to work at the design level, but then we have to work at the concrete level, where again, we can make savings of in the order of 30% or so. And then we need to work at the cement level. And if we combine all these together, we really can make very substantial reductions. We can do these with existing technologies. We can do them fast. We can do them at large scale. But, we have a lot of effort being diverted by people who think they can come up with miracles which can just sort of make this all go away. That's why I have to say we have to face the fact we can't have zero carbon concrete without stopping CO2.
Now we're getting back to where the controversy really exists, and I've held off Peter Fikowski as long as I can. I can't hold him off anymore. Peter, take the mic.
Right. Thanks. Yeah. So Karen, as I said, your point about cement is excellent. There are a lot of attempts to reduce the carbon emitted in cement production, and they're nice, but they're not huge, as you said. The key thing that you're perhaps overlooking is the rock. The most of 80 to 90% of concrete is actually rock, and if you imagine an oyster shell, on your dinner plate, that rock, the calcium carbonate rock, is essentially manufactured by a small animal, and there's a company here in Silicon Valley, Blue Planet, which does similar chemistry, creating calcium carbonate rock, but they can actually engineer it for the porosity desired and the density.
Yeah. Well, I think that's probably, where you and me seek to differ. Yes, of course, limestone was created by lots of little animals sequestering CO2 over millions and millions of years. The problem is they also need calcium to do that. And if you calculate the amount of calcium in seawater and you work out the volumes of seawater you'd have to process to get meaningful amounts of limestone, you just find out it's colossal. And the cost of that would cost you roughly 100 times what it costs us to produce cement today. In fact, the person who has this Blue Planet company, he previously, for about 30 years, had this company called Calera, which tried to do this. And I think over 30 years, he failed to deliver on these promises. Now he's formed this Blue Planet. And if you calculate the kind of cost he needs to make these synthetic aggregates, it's roughly about 100 times the cost of natural aggregates. How are we going to, you're going to increase the cost of concrete by 100 times, which I think, even though it's very cheap product, I don't think most people could afford to pay 100 times that. And, we have to benchmark these ways of sequestering carbon against, other technologies. And there are other technologies which can do this a lot more cheaply. I think we are going to have to get CO2 out in the atmosphere, but we need to say this is going to be a very costly operation, and we need to see how we can get rid of most CO2 for the lowest price. And, certainly making synthetic limestone from seawater and CO2 is not going to be the cheapest way to do it. It's going to be about 100 times more than other off-the-shelf technologies.
The source of calcium, there are many sources of calcium. In terms of cost, all the experts thinks it's a profitable business. They're raising money from cement makers, from concrete makers, who understand the process soup to nuts. Again, I understand your academic expertise is probably better than that of the corporate leaders, but there's a difference of opinion there.
Adele Buckley.
Yes, well, excuse me. I have heard Martin tell us that something like garage floors in buildings in Ontario are incredibly over designed with respect to concrete and rebar and so on. How can we reduce this overkill with the rebar? That's one question. And the second is where do building codes come in? Because I think everything is built according to building codes, but they could be modified to better support the CO2 situation. On the other hand, all I hear from Martin is that instead of adhering to the building code, which is conservative, most buildings are built way over necessity.
The building code is a guide, but the regulation in Toronto is ill-conceived based on a treatment plant downtown and a number of tower cranes that exceeds any other city in North America. So I know Toronto very well. I've been doing below grade work there a long time. And the fact is that those are pre-consolidated soils and nobody tells you how to design it by the building code. They tell you at the City of Toronto. And that's why the City of Toronto, which requires a hydrogeology report and really just said you have to keep all water off site, when that's not realistic. So I designed a system called FEH to Old Lock, which is a patent now, and that will drain behind and reduce footprint. So I work on things like that. But I'm not here to market my patents, but that will become the norm in Toronto again, because developers need a break. We have developers that have land that's gone down, and we're going to see a lot of problems with housing in Toronto if they can't get that thing figured out. And they say that the city limit requires a water management system. So this is an alternate water management system, and it's based on my experience. It'll work. And
everything south of Front Street in Toronto is reclaimed land with significant groundwater. And some of those buildings where we're having a significant development boom have pumps running in the basement 24/7 because the lake is coming up through the foundations. That reclaimed land is less than 150 years old. There's also buried rivers throughout the downtown core. So the hydrogeology plans, I think, are attempts to mitigate the existing groundwater situation. And I can't imagine just pumping the water from standing groundwater on reclaimed land out the back. You're going to have it go directly back into the foundation.
So I'm familiar with south of Front and north of Front. I did the foundation on the Sky Dome in '86, which is south of Front. That excavation was dry. Now, if you get down to Queens Quay and whatnot, I wouldn't recommend the use of an alternate water management system. But it's really a case of 80% of the sites in Toronto are vastly over-designed, and including our subways. Like our subways are over-designed. When you've seen it before, it's hard to watch. It's hard to watch the waste. I appreciate what you're saying south of Front, though. And, I don't think that's the best place for a target project. I'm going to do one at 300 Bloor West, which is virtually dry.
How much it is possible to lower the carbon footprint of concrete by injecting carbon CO2 in some form. There are some, I know you, Karen, are pretty adamant about you don't trust the Blue Planet approach, but there are a number of different other companies doing other things. And I don't know why they're so secretive, but they don't like to be interviewed. When I've tried to reach them and ask them to be part of the conversation, they never join us. But there are companies that do things like make concrete blocks and put them in some sort of enclosure for curing and then inject CO2 into the air in that enclosure. So they presumably absorb CO2 while curing. And there are others that just squirt CO2 into the mix, the liquid concrete, as they're pouring it, etc. So I don't have any awareness really of the details about how effective this is. They are not claiming to be carbon negative, but
No.
they are claiming to be low carbon concrete because of this procedure.
Comes down to cost benefits analysis. You know, if you talk about this technology, which is actually commercialized by a company called Solidia, which hardens blocks by carbonation. Yes, this is fine. This does absorb some of the CO2 that was emitted in the process of making the cement. And then, you know, you have a product which has somewhat lower CO2. The point is that in the current technology, these kind of products are not going to protect reinforcing bars. We've already talked about reinforcing bars. And for structural concrete, you know, this is still the best option out there because you have a very good match in terms of properties between steel and concrete. They actually do have the same thermal expansion coefficient. So that's actually why they do work well together, even when the temperature goes up and down. And that's not the case for other kinds of reinforcement. Things like basalt fibers can be very good for crack control, but you would have to redo all the structural designs to be able to build a skyscraper out of that material. So these products do lower CO2. They can be used in a limited sense. But if you take this example of blocks, you have to have a block factory that already has a a chamber usually used for curing. And this exists in, you know, some places like North America, but in the vast parts of the world where blocks are made, like India and Africa, they don't have these curing chambers because the ambient temperature is already warm enough to not need them. So this is a reasonable technology, but has a limited application. Now, as for the thing of squirting CO2 into concrete, that's a little bit more controversial because the actual CO2 you capture in the concrete is really, really, really tiny, fractions of a percent. So it's really almost negligible. And it's claimed that this then improves the properties of the concrete, but there hasn't really been independent verification of this. And as I said, it comes back to this question of how much CO2 can you capture for a given amount of money. And both of these technologies end up being fairly expensive ways to capture CO2 compared to other solutions out there. You know, just capturing CO2 and stocking it underground. One of the best ways to reuse to capture CO2 is to reuse demolished concrete. This is an incredibly good technology because a lot of that cement in the concrete has not been carbonated. And if you can separate out the aggregates, reuse the aggregates, then take all the fine materials, you can use it in two ways. You can use it either to make new cement, or you can actually carbonate it further and use it as an addition to cement. Both of these are very cost-effective ways to use the potential of that concrete to take back some of the CO2 it gave out when it was originally produced. But they're not carbon negative solutions.
Okay, well, that's interesting. Now because, you know, the thing that Blue Planet does is it uses demolished concrete as the source of the calcium. It captures and smashes old concrete and mixes it with CO2 from a flue or a smokestack nearby with presumably some other chemicals. I don't know what. Yeah. But that's how it makes the aggregate that then is a substitute for the gravel or the limestone stuff that is normally used as the aggregate in concrete, which is something like, is it 70% or so of the component of real concrete?
But the problem again there is it makes a very expensive aggregate, which is actually not a high quality aggregate neither. So, you know, we should use that demolished concrete, but we also have to bear in mind that the amount of that concrete we have is quite limited. You know, we can only at a maximum mop up about 1% of emissions by recapturing a concrete. So we should certainly do these things, but it's not going to totally solve the problem.
Okay.
Yeah. Yeah, obviously, Karen and I disagree on reality here. I'll show you a few slides of the plant. So here you can see there the Blue Planet plant, the power plant they're getting CO2 from is in the background. And one point to get here is that the investors, who, as I said, are power companies, they're cement companies, they're equipment manufacturing companies, they're even quarries investing. I trust them. I've gone over the numbers myself, but I'm a physicist, so I don't trust my personal analysis, but I trust the experts. And so in the background, you can see the pipes coming in, just part of the process. They're capturing the CO2. I don't have the slide handy, but the mixture is in the tank here, and then the limestone they create gets filtered out in these, and here's some of the limestone they're creating from calcium. In addition to, as Karen said, that they reuse the existing rock and the existing sand, but a lot of the calcium is still available in the cement and the demolished rock, demolished concrete. And here's some of their final product. And here's the pipe coming in from across the street. So it's just a matter of opinion of, do you believe the people who actually manufacture it and they're expecting it to be zero cost? They started this before there was any 45Q benefit here in the United States. So this was profitable without any cost of carbon. And in fact, the power company is not paying them to take the carbon away. They're just taking the carbon as a free resource. And then they, of course, get paid by taking some of the remediating the concrete. Anyway, but it's I think it's fine for us to disagree about the finances of it.
Do you know how much they are able to claim that they can do this for, Peter? Have you asked them about the cost?
Oh, yeah. Yeah, so the quality of their concrete, they've been using it at San Francisco Airport, and of course, the San Francisco Airport is not going to use low quality concrete, and so they certified it that it was absolutely high quality, and they sell it at a competitive price. All of their output is called for over the next several years. So there's no cost, is the point, is that they actually earn money selling the carbon negative concrete. It's about 1,000 pounds per cubic yard. The concrete here is expensive, right? So we don't have quarries in San Francisco or even very close. And so the very high quality concrete, it's light. They specialize in lightweight rock, which you use in skyscrapers and overpasses. And that tends to sell, if I can recall, for $100 a ton, or even more than that, as opposed to if you just go to your garden shop, rock can be as little as $30 or $40 a ton. But for high quality, it's $100 or $200 a ton, and that's why it's profitable.
Is that good or bad? I don't know what.
It doesn't matter. The point is, it's profitable. Now, if you take today's process and you move it out to Kansas, somewhere where land is cheap and they probably don't mind opening up quarries, it's not going to be profitable yet at today's process. In the future, it's likely that the technology will improve. It always does. At which point it is likely to get competitive even in rural areas.
Martin, your
Yes.
comments.
Yes. So I disagree with Peter, and it's based on science, but it's not really opinion, it's experience. You know, the amount of concrete, amount of kilograms per cubic meter in a 30 MPa concrete in Toronto is 350 kilograms, and with a nanocolloidal silica, or 450 kilograms. With a nanocolloidal silica, we actually get that down to 325, and that makes the price competitive. And the nanocolloidal silica is an internal curing. Even the concrete you're talking about, Peter, could benefit from that because it wouldn't need any curing. It removes wet curing costs. And but I go back to the rebar. You know, the idea of rebar wouldn't go down with a carbon captured concrete, and I don't think on scale you can do that technology. Based on what I've read about it, I mean, Bill Gates is pushing it, and I don't really think he's doing it for any other reason than to create a smoke screen or whatever. He's got lots of money, but I really believe that CO2 is best helped with the right mix.
Yeah, tell me what Bill Gates is doing. I don't know anything about that. I like to hear about Bill Gates's adventures.
Well, I think he's backing carbon capture as a technology.
Direct air carbon capture, isn't he? You know, which is extremely expensive.
Yeah.
Mm.
He doesn't know anything about concrete, but the fact is that people who are using internal cure silica are claiming that it'll give it a 1,000-year life. And I go back to the idea, Peter, of getting rid of rehab. I mean, why have an expensive mix? People won't buy it. They won't buy an expensive mix. Everyone cares about money. So if we can get the cement down and make it last longer, that's the value. Value engineering is functionality over cost.
Martin, I think you're making the very good point of both and. Obviously, you always want to use a better cement. You always want to use a better mix. Reduce the steel, reduce the cracking. You want to do that. If the aggregate you use happens to be carbon sequestering, that's good. If it's too expensive, then no one's going to buy it. It's a moot point. I don't think any of us are going to be issuing any multi-million-dollar contracts. So, and it'll be several years before the Blue Planet is available at large scale. So I think we're all pretty much on the same page, as long as you, instead of saying either or, you say both and. Of course, you want to improve the use of the concrete and optimize it. And of course, as far as you can get synthetic limestone and capture CO2 from somewhere, and in a way that's cost effective, then you should do that. Here's what I think a big takeaway, and it's implied in everything we're saying, is that the best way to do it is not so much with a price on carbon.
I agree with Peter in the sense that we shouldn't price carbon, but go ahead. I think Adele was going to say something. Adele.
Yeah, well, I think I have some more questions for Martin, because he's talking about concrete in the area that I live in Canada, whatever. Are companies at all conscious of trying to reduce CO2 in their product? It seems to me that there's a lot of publicity, but trying to, but there's a lot of greenwashing and no actual reduction. But so that's one. Is there anybody trying to actually reduce the CO2 in real life? And second, what would make anyone stop overkill and using twice as much concrete and rebar as is actually needed? And is this controversial? I mean, we certainly know about collapsing buildings. They come in the news when it happens, and everyone wants to avoid the possibility of that happening. So how could you get motivation to stop the overkill when meeting the building code apparently is sufficient.
It is overkill, and we do it one step at a time. I try to advocate to make the problem smaller first before you can get your arms around it, before it can go away. Cost is always a factor, and I think Peter recognizes that if we can get the best technology today into the cubic meter of concrete in Toronto, then people are going to be able to use different systems. And so if they can pick different systems, for instance, precast is moist cured, but we're testing precast with nanocolloidal silica without any moist curing, and think of all the energy involved in moist curing.
Hold on. What is precast?
Precast is when you create certain members that are done in a plant, shipped out like a bridge girder or whatnot. And traditionally they're highly porous. So, we can do a better job and not have the energy of the steam. They do steaming to try and get that thing cured. And when they cure it, then they ship it. So they want to have a turnaround in a plant environment, and they put it on trucks. And precast is a good product. They just have to change the mix design. In ready-mix plants in Toronto, they have not all ready-mix plants in North America, they have a certain process. They have mixed water, they have dry and mix. So if you can improve work with their existing process and make them realize that this is a better concrete, get rid of the crack control rebar. I go back to that because it's a big problem. There's still people doing slabs with rebar in them that they don't need to. They don't need to put the rebar in the slab if you don't have to do a saw cut after. Why do you need the rebar? We're seeing no cracks. The benefit of basaltic fibers is it's inert and it's the same density as concrete. So it behaves better, and you can deal with it without any cover. So Roman concrete was done with a pozzolan, and the pozzolan is basically,
What's that?
well, we've got a pozzolan is a fly ash that's very, very fine grained from volcanic events. And so that concrete's still around. And so my goal is to try and prove that, we can do 1,000-year concrete. That's my goal. And at least I can make it waterproof.
Well, Martin, hurry up.
Yeah. Well, I have a mixed design that I can be happy to send to Pugwash Group. And
Well, yes, but
anybody
now-
on this video.
How many things are created that anybody's going to want to live in 1,000 years from now? I mean, I don't know how much to worry about the fact that the lifetime of concrete structures is not comparable to what the Pantheon looks like 1,000 years. So I don't know what to worry about, because maybe people would be digging up the sidewalks anyway, or maybe if they design a building, they're not going to want that building much more than 50 years, and they would tear it down anyway. So is it important that we get concrete that's going to last a lot longer?
Well, it is for the 25-year rehab that we're seeing on the bridges in Toronto. And
25 years? Is that how long?
25 years, they start to go at it again. You see them starting to chip and do the work again. It's pretty hard to fix the concrete when you didn't do it right to begin with. You end up with putting patching on everything, and that internal structure is the mistake. So when you use a nanocolloidal silica admixture, it's very, very tight waterproof concrete. We can get away without any waterproofing on basement walls in Toronto. So I see the multiple layer benefit to the person who's the developer. And
Most of these
I really
companies,
don't need 1,000 years, but unfortunately, if you put this mix together, that's how long experts are saying it'll last.
Yeah. And Meta,
I use it. Yeah.
what's wonderful about what Martin is saying and what he's doing, and I think we really want to encourage him and his colleagues, is we'd forgotten a lot of what the Romans learned about concrete. And Martin, correct me if I'm wrong, but the cost of doing the concrete right is probably lower than the cost of the way we're doing it now. Is that correct?
Yeah, my goal is to change it out without an increase in cost. You know,
Right.
when we sell it, like for instance, the nanocolloidal silica admixture is from one supplier is $50 US a gallon, and from another supplier is $25 US a gallon. So I recommend it $25 US a gallon, and I try to specify the nano size, where I would say, you know, in my shotcrete on this system, I'd like this product, and I'm going to make you use basaltic fibers. And so we prove one job at a time in civil engineering. And for sure, we don't need 1,000 years. You know, I hope we're all around in 100 years. I mean, you know, the problem we have is extinctions and all these different things. So it's, I'm a big sustainability guy, Peter, and I appreciate where you're coming from as well, because, you know, it's a multifaceted problem, but if we make every facet a little bit better tomorrow,
Yeah.
then we're doing what we can as human beings, right? So.
And Martin and
What
Meta,
can be done to make it move into common practice, some of these things that you're talking about. I mean, they're just limited examples. And you know, if we wait long enough, maybe everybody will do it, but we might have expired from the heat by then. So we really need to move it along. How do you do that?
Well, I'm hoping that by being vocal, by what Meta's started here and what Pugwash is picking up, that Pugwash, I think, is a group that the government may pay attention to. I don't believe that the government wants to have rehab after 5 years or 10 years on their bridges. There's a lot of federal bridges. And so we get the word out, like in Indiana and Ohio, they've done 350 bridge deck rehabs. And I could look at their bridge deck rehabs and I could improve it further. You know, they're still putting green rebar on the base of the deck at quite a large volume. And realistically, the best bridge deck rehab is an ultra high performance concrete called Cortuff. Mm-hmm. So that product goes on with 2 inches thick and it replaces the rebar, even though the product is probably $1,100 $1,200 a yard or something. It's just going to last forever. So speed is important. You can pour that as a liquid, and it's a very interesting product. So I try to study the best products, and I try to recommend something that has a value point for functionality. So based on experience, we see a lot of below grade mistakes. If we don't really have the problem with a high rise. A high rise is covered in a cladding, and it's pretty efficiently designed. We could probably get rid of some of the flooring problems. Like, for instance, flooring in slab on grade is a $3 billion a year insurance problem in the US. So we can get rid of that problem with nanocolloidal silica. You know, I try to hang around with the experts, and I ask them good questions. So the idea would be, you know, can we get everybody's input and do it expeditiously? I think, you know,
Let me ask about these concrete blocks, because most of the companies that I've looked into, I can't interview anybody, they just won't do it. But that the ones that claim to be low carbon concrete are making concrete blocks. Now, I just don't imagine that there's a whole lot of use for concrete blocks. I mean, you can't do highways that way. I don't think you can do bridges. What can you do with concrete blocks? And how far will that go in solving the problem? Let's assume that you could make concrete blocks that really are quite low, unusually low in carbon. Then the carbon footprint in general. Would it solve much of our problem?
Concrete blocks won't, but because you need to have an assembly that can carry the tension and compression rebar into a larger design. The concrete block is a piece of precast, Meta, to give you an idea. That's really precast, and it's a good idea to perfect every piece of concrete. And if it lasts longer than we're going to last, you know, I mean, I don't think the Romans thought of that, but You know, there's they did the best job they could with what they had to work with, and they didn't use rebar. They used arches and different innovation design. But the nanocolloidal silica is an engineered polymer, and nanotechnology is in our world now, and so that benefit it's quite inexpensive. You know, I believe that we can get this concrete right and get rid of the tension or the crack control concrete, which is a big thing, or we can get down the number of kilograms per cubic meter. If we can go from 450 on shotcrete, which is sprayed concrete, to 325, and we're testing at the University of Windsor. And I believe, Meta, we can give you some names for some future shows and move this thing towards a value. It doesn't have to be me presenting. There's other people who say what I say. I mean, you know, this is becoming common knowledge that concrete's too porous. And I think the ready mix plants, if we can give them a process that doesn't change the way they make a concrete truck, right? If we can still pull up a concrete truck, the fact that they're going to sell more of them, apparently there's a cement shortage anyway. I think you might be aware of that, Meta. There's a cement shortage.
No.
Yeah,
No,
there is.
wasn't. Okay.
My calculation is that 40% of the CO2 problem is from the built environment, and 20% of that is concrete and steel.
Well,
It's
so
just-
now let's just sum it up by saying how much, if everybody took your best advice and we had the optimum materials to use, and everybody did the perfect thing, given the information that we have now, the state of knowledge, how much could we reduce the emissions? Presumably, you don't believe it's possible to be negative, but if you just look at reducing the emissions, how much can we take out of carbon emissions from the manufacture of concrete?
Well, it's cement, but
No, the whole thing.
yeah, well, I would say the 40% of the built environment percentage, I think we could get to 30. So if you know, chances are that that's going to be done over the next 10 years. I think it's unavoidable that people are getting aware of these better mixes. And I'm not the only one doing it. It's more prevalent in the States. And as Canadians, we can be leaders. You know, I talked to a value engineer this morning who's quite popular in Toronto, and a lot of developers use them. And we're gonna work together. We made a deal. We're trying to work together. And he's going to mentor me a bit on how to get my patents going. He's got several patents. So I think patents have to be priced reasonably. You know, Trudeau did one good thing. He allowed patent review in 4 months, and that got an examiner on. And so we took advantage of that program. And then now most patents that are done in Canada are
Why should we care? Why should I care whether patents go through quickly or take a long time?
Well, I think there's some benefit to me moving on to things other than making patents and arguing with examiners, perhaps. But I just want to see. I think where my heart is I think where Peter's is. You know, I think he's an environmentalist, and so we need to be more care about the environmentalism. I mean, we end up with people saying there's no CO2 problem. You know, that's the thing you get.
Funny question. Who are the decision makers? Because those are the people and groups that we have to get at. It doesn't sound like it's the province here in Ontario. It sounds like it's more like the city.
Adele, that's an ideal question. And when it comes to, there are two issues. You know, Martin is talking about the quality of concrete, which we just finished remodel here, and there's a lot of concrete used. And I wish Martin were here to redesign it. That notwithstanding, when it comes to climate, the issue, Adele, is our goal. And the UN goal has been to stabilize CO2 and greenhouse gas levels. And most of us really want to bring the CO2 and methane back to levels that humans have survived and presumably can survive. Today, CO2 levels are 50% higher, 40% higher, 40 to 50% higher than humans have ever survived long term. And academics think, well, the academics justify it. They say, listen, it could be worse. And every bit of emission we don't do makes it not so bad. Presumably, we can survive a little longer. Those of us who are parents and grandparents, it looks like we're mostly grandparents here, although Tariq, your hair's not very gray yet. We're really concerned about our children and not emissions. And so the critical thing, Adele, is to get the UN and get Justin Trudeau to talk about climate restoration, that what's really important is the survival of humanity. And that's the level, not emissions.
I agree with all of that, and we probably know that too. But I want to know who are decision makers with respect to concrete.
Okay, that I can't answer.
Martin probably has some answer to that, but Meta wants to.
And with that, I'm going to go. Thank you.
A key question, I think.
Thanks, Peter.
Yeah.
Yeah, I think that the decision maker who could make a difference would be somebody like Trudeau. So at a federal level, they could mandate the use of the right admixtures. That's pretty simple. I mean, people are just going to do it overnight. And I don't need to make any money off the admixture. Somebody will make some money off it. But, you can get tanker loads into Toronto of nanocolloidal silica, and you can adapt it into the existing plants without a lot of money. There's no money, really. It goes into the mixed water percentage. So you put about, I'm going to say it on this video, you put about 10 ounces of what's called internal pure silica per 100 pounds of cement, but you can reduce the amount of cement. So my goal is to try and see how this prices out so it doesn't increase the cost of the concrete. And why can't we mandate it? It's not like they need to put that much concrete in. It's a start, right?
Keeps us posted, Martin. If you know you're on the track of solving it, well, good for you. Time's up.
Yeah.
It's been
thanks, Meta.
Yeah, thank you very much. Appreciate it, and we'll be back in touch with everybody, I'm sure. Thank you.
Nice
Thank you. That was a very informative discussion. That's why I kept quiet, because I was listening to all of the details. It was way beyond my level of contributing anything. But thank you.
Anyway, call anytime.
All right.
Thanks very much, Meta. And thanks for what you did. Thanks for what you did, Meta.
Project Save the World produces these shows, and this is episode 541. You can watch them or listen to them as audio podcasts on our website, tosavetheworld.ca. You can share information there about 6 global issues, too. To find a particular talk show, enter its title or episode number in the search bar, or the name of one of the guest speakers. Project Save the World also produces a quarterly online publication, Peace Magazine. You can subscribe for $20 Canadian per year. Just go to pressreader.com on your browser, and in the search bar, enter the word peace. You'll see buttons to click to subscribe.